Hey guys, today what we're going to talk about is something called the central limit theorem, and we're gonna be using a couple of different things to demonstrate this today. So first thing I'm going to do is I'm just going to kind of read through the central limit theorem, talk about what it's saying, and then try and demonstrate it with an experiment or a simulation so that you can understand how it works. But the central limit theorem is one of the most important theorems that we have in statistics because it allows us to take any distribution or any spread of data, no matter what shape it is, and turn it into something that is normal. Okay. And once we turn a distribution that maybe starts off as something that is skew left or skew right, and we can normalize it using this theorem, then we can use things like normal CDF or inverse norm to calculate probabilities. All right. So it gives us a lot of power. All right, so let me read this thing real quick. It says the central limit theorem states that if you have a population with some mean and some standard deviation, and you take sufficiently large random samples from the population, then the distribution of the sample means, and this is where I want to pause. All right, so this thing that they're talking about here, these sufficiently large random samples from the population and the distribution of the means of those samples. What they are talking about there is something called a sampling distribution. Okay, so in our population, we have all this data. We're going to go into that population and we're going to take a sample, but we're not going to take one sample. We're going to take many, infinitely many samples. Okay, and when we take one of those samples, we're going to take those pieces of data that we selected and we're going to average them. We're going to take the mean of them. And we're going to do that over and over and over again. All right. So if we do that, what happens is it will become approximately normal. The distribution of all those means that we take will create a normal distribution. All right, so let me demonstrate what that means. And to do it, we're going to go to My Open Math here, and you'll see underneath where it says watch the videos, this sampling distribution simulation. I want you guys to click on this so that you can follow along. You guys can play with this as well, but it gives you a really good way to experiment with sampling distributions. Okay. So I already have it open up here. Let me do it again so you can kind of see what you're supposed to do. So I'm going to click on that. You'll see this menu here. We're looking at sampling distributions right here. And we're going to do sampling distributions of the mean. Okay, we'll click on that. And it'll bring up a graph, and you'll see over here that it gives you some different options to play around with here. And what we're going to do is I'm going to select baseball player salaries in millions. We'll do first edition. Okay. So it creates a population for us to experiment with. All right, so we have this population of all baseball players from 2012, and we have all of their salaries stated in millions of dollars. And we can see the actual data here if we click on Show Data Table. So you can see like A-Rod made $30 million, and Vernon Wells made 24.19, and we have every single baseball player in the league and all of their salaries. So this is a population that we can work with. Okay. Now, if you look over here on this part of the screen, it shows the shape of the population. Okay, so this is the shape, and you can clearly see the population is skewed right, which kind of makes sense. Most baseball players do not make a whole lot of money. So you'll have a whole lot of baseball players over here on the left-hand side making a little bit of money. And then you have a few baseball players over here that are making like really big bucks, right? So it makes sense that it's kind of skew right here. We also get a mean and we get a standard deviation for that population. Okay. So let's go back to our notes real quick, and we're going to kind of scroll down here. And what we want to pay attention to really understand the central limit theorem, we want to understand what happens to the shape of the distribution and what happens to the mean and the standard deviation of the population. Okay, so we're going to kind of observe all three of those things at once as we run through the experiment. Let's go back here to our thing. All right, so what we're going to do, and you'll notice back in the notes here, we're going to take samples of size 10. All right, so we're going to set our thing here, right? Choose samples of size 10. So what that means is they're going to go into our data, they're going to go into here. They're going to randomly select 10 players from the population. They're going to take their salaries and they're going to average them. All right, they're going to take the mean of those 10 salaries. Okay, so we're going to generate one sample. Boom. All right, so it randomly selected 10 players, and we can even see the 10 players that they randomly selected if we click over here on Show Data Table. You can see the 10 players that they selected, and they took the average of these 10 salaries. And the average was 2.968, and it plots that down here on the dot plot. And then I'm going to do it again. I'm going to put those 10 players back in the population, and I'm going to randomly select another 10. And you'll see I got another dot here just above 3 million. So when I took the average this time, we got just above 3 million. And I'll generate another one, and another one, and another one, and another one. And I'll keep on doing this, right? And as I do this, it starts making a distribution of these dots, right? You could also do this with a histogram or some other graphs as well, but the dot graph will work just fine for us to see what happens with the shape here. Okay, and I'm going to start generating them faster. So instead of generating one sample at a time, I'm going to generate 10 samples, right? And I'm just going to keep clicking in. You can kind of see how many samples you've done, and it keeps track of the mean and the standard deviation for this new distribution that we're going to see. Okay, and I'm going to start generating them even faster, right? I'm just going to generate like hundreds of them and thousands of them. And you start to see the shape of this thing, okay? It starts to kind of take form. All right, so let's go back to our notes real quick. All right, so from the population, all right, we started with the population. Population looked like this right here, extremely skew right. All right, so I'm gonna draw that population distribution here. Right, and I'm gonna draw a very extreme skew right distribution. Right, and I'll note that shape, skew. And then I'm going to go here and I'm going to note the mean and the standard deviation of the population. Okay, so I'm going to say the mean was 3.439. And the standard deviation for the population was 4.698. Okay. And I'm going to go back to my sampling distribution. And remember, we took thousands of samples of size 10 here to generate this thing. And I'm looking at my mean. Okay, we got 3.429. Okay, so I'm going to write that down here, 3.429. And the standard deviation, which is right here, they call it a standard error now, 1.453. And I'm going to draw my new shape. All right, so you'll notice this was the population. This is our sampling distribution with samples of size 10. Remember how it was like extremely skew right? Well, when we look at this, it has kind of, it's not as skew right as it was before. It's still skew right, but not as much as it was before. All right, so it's lost a little bit of its skew. All right, and so now when I draw this thing, it now has like a visible tail on the left, but it's still skew right. All right, so I'm going to draw it with a little bit less skew. All right, so we're going to say less skew than it was before. Okay, and then I'm going to look at the mean. All right, so the mean was 3.439 in the population. It's 3.429 in the sampling distribution, so it didn't really change. The mean stayed the same. Okay, the standard deviation 4.698 to 1.453. It reduced a lot. Right, so the standard deviation is going down. So what we're seeing is a lot less dispersion in the data of the population than what we're seeing in the distribution of the means. Okay, so now let's pump up that sample size to 30. Let's see what happens when we go to 30. And don't forget what our theorem up here said. All right, and it says that if we have a sufficiently large sample, right? So if we have something that's 30 or greater, it should become normal, right? It'll be approximately normal when we have a sufficiently large sample, all right? So let's see what happens with our experiment, right? So I'm going to reset the plot. I'm going to change the sample size to 30, and I'm going to generate, right? So I'm going to generate one sample at first, right? So what they did was they went in here, they selected 30 players, They averaged those 30 salaries, and we got 2.395 million. Okay, and I'm going to generate a little bit quicker here. I'm going to generate 10 at a time, right? So they took 10 of those samples, right? And then do hundreds of them, and then we'll do thousands of them so that we can see that shape start to generate. And I'm going to get this up to about 10,000 here so we can see what's going on. There we go. And take a look at that shape. Almost all of the skew is gone. It's still maybe slightly skew right, but it is almost perfectly normal now. And I'm going to go to my notes here and I'm going to draw that out because we can see that nice normal shape. Okay. So at this point, now that the sample is 30 or more, we have something that is approximately normal. Okay. And let's go ahead and note the mean and the standard deviation that we got. So we got a mean of 3.444. And we have a standard deviation of 4.698. Okay. So, oh, did I read that wrong? I did. I read the wrong one. 0.844. Sorry. We got 0.844. Let me just double check that. Yep, 0.844. All right, so there we go. So again, looking at the mean, 3.439, 3.429, 3.444, the mean is staying the same, right? No matter how large we make those samples, but the standard deviation is changing. It is getting much smaller as we increase that sample size. And there is actually a formula that we can use to calculate this standard deviation. And I'm going to share that with you now. Okay, so if you have your pen and paper ready, these are the kind of things you might want to jot down. All right, so the way that this number is calculated without having to run an experiment or a simulation, you can take the sample size and the standard deviation. All right, we're going to take that population standard deviation and we're going to divide it by the square root of the sample size. Okay, so let's say square root of n, right, for general formula here. Right? So in our case, for this experiment, we're going to take 4.698 and we're going to divide it by the square root of 10. And let me show you what happens on the calculator when we do that. We should get something close to 1.453. Yeah. All right, so we got 1.485, 1.453. See, it's really close. And data is never going to be perfect, but this is the formula that will calculate that new standard deviation for you if you don't want to have to sit there and run the experiment every single time. Okay, and I'm going to try it again for this one. So for this one, the sample size was 30, so we're going to start with that 4.698, and this time I'm going to divide by the square root of 30, see if I get something close to 8.844. So I'm going to come over here, move my calculator, and we're going to say 4.698, and I'm going to divide by the square root of 30. Yeah, and we got 0.8577, so pretty close to the 0.844. If I had kept on hitting that button and generating thousands of more samples, eventually that would have converged exactly on that number. Okay, some other things to note of what we saw there with the standard deviation and the mean. Notice that the notation changed, right? So when we're talking about the population, it's just mu, this little Greek letter mu. But when we move distribution, it's no longer the mean of the population, it's the mean of the means. So that's why you see a mean with a subscript of x bar, because it's the mean of the means of those samples of size 10 that we took. Same thing with the standard deviation. We're no longer looking at the standard deviation of the population, we're looking at the standard deviation of the means. All right, so that's why they changed that notation on us there. Okay. Let's go down here. So remember what we did was we started off with something that was not normal. We started off with something that was skew right. And by increasing that population, we got to something that was normal. I'm sorry, increasing that sample, we got to something that was normal. But what if we start off with something that is already normal, right? So we're going to say, well, what happens to the shape of the sampling distribution when the shape of the population is already approximately normal? Okay. So I'm going to start over here. I'm just going to go ahead and draw something that is approximately normal. Okay, so I'm going to draw a nice normal curve. Forgive my drawing. I'm using this new pen and tablet thing, which I'm not so great at yet. There we go. So we got something that's approximately normal. This is what we're going to start with. All right, and we're going to go back to our simulation here. Let's reset the plot, and we're going to choose a new data set here, and we're going to go to, I think it was Olympic Marathon. Yeah, first edition Olympic Marathon. And when you look at the population, this was the closest one that I can find to something that was approximately normal. It looks like it has a little bit of a skew right over here, but this was the closest to normal that I can find of the options that they gave me over here. So we'll kind of start with this. All right, so we're going to say this is approximately normal to start with, and then we're going to go ahead and do a sampling distribution on it. All right, so note the mean 141.059. I'll write that down here. And I'm gonna get the standard deviation, which was 7.438. Okay, and then we're gonna go ahead and do our sampling distribution of size 10. Okay, so I'm gonna make sure my samples are starting off size 10, and they are. I generate one sample. Okay. So what they did was they went into the data here, they randomly selected 10 of the marathon runners, took their times and averaged them. That's where this dot came from. So they got an average time of 140.196 from our sample of 10. Do it again. We take a different 10 runners, we average them, we got something that was a little bit greater than 140 there. Okay, so I'm going to start generating them faster so I can see how the shape of this distribution forms, and I'm going to generate hundreds and then thousands, and we'll get it up to 10,000 like we have been for the previous examples here, right? Because you really get a good sense of the shape when you start getting right around 10,000. You start to get a nice shape, and there we go. All right, so we started off with something that was approximately normal, and when I look at this thing, it is again very normal. Okay. Now, it's hard to see with the way that they have this scaled, but notice that in our population, we started off at like less than about like over here at 126, and then it went all the way up to 161. So when we look at this, right, we're not at 120 something here, we're like at 130 something over here, and this extends to about 147. So what's happened is the dispersion has tightened up, okay? So when we draw our new shape, right, we're going to still draw something that's approximately normal, right? But it's going to be a tighter curve, right? A skinnier curve. The data has become more compact, right? So what happens with the shape here is it stays approximately normal, but it's tighter, for lack of better words, right? Less dispersion. When we get something that is tighter than it was before. All right, now our mean 141.060. Was that 060? And standard deviation 2.187. All right, so 2.187. So again, we're observing what happens to the mean. 141 to 141 doesn't really change, just like in the previous example. That mean is going to stay the same, and that standard deviation is going to get smaller, right? We're going to see less dispersion in the data. It got a lot smaller, but it's still following that formula where we take the population standard deviation and divide by the square root of n. That's how you would get that number. Okay, we're going to do it again this time for samples of size 30. So I'm going to reset my plot. I'm going to change this to 30 this time. There we go. So now it's on 30. I'm going to generate a sample and see what happens, right? So I take 30 of the runners this time, average them, I get 141.652. And then I'm going to start generating it faster, so hundreds and then thousands, and we'll work our way up to about 10,000 here. So there we go. We see a beautiful normal curve here. So I'm going to go draw that. But pay attention to what happens with the dispersion. It's at 1.054 now. We were at 2.187. So we got a tighter curve than what we started off with, right? Because it went from 7.438 down to 2.187. So this is a tighter normal curve. This one's going to be even tighter. It's going to be even more skinny. All right, so I'm going to draw a nice, really tight normal curve, right? So it's still approximately normal, and it's going to be really tight. Again, for lack of better words, right? So it gets skinnier as we go. The mean is going to stay the same. It's going to stay, this time it was at 141.052. So we're not seeing a whole lot of change here. So 141.052, and our standard deviation was at 1.054. All right, so again, we see that standard deviation drop again because we increased that sample size. Okay, so what I'm going to do next, I'm just going to kind of summarize what we saw here. Let me grab my panning hand here and get some space. All right. So what we saw with the shape, right? We talked about the three major characteristics. What did the central limit theorem do to the shape by taking sampling distributions? Right? The distribution normalizes. And this only happens if one of two things, or if one or both of these things happens, right? One, the population is already normal. And two, if n is greater than 30. Okay? So either the sample size has to be large enough or the population had to start off as something that was normal for this to happen. Okay? The center, it stayed the same. Okay? So in other words, the mean of the population was the same as the mean of the sampling distribution. Those stayed the same. Then we talk about the spread. Okay? The spread reduced. Okay? So as we increase that sample size, right? So as n got bigger, right? As n increased, right? The standard deviation decreased. Okay? And again, I apologize for writing all weird here. I'm still trying to get used to this tablet. And the way that we calculate that, right? So we start off with this population standard deviation, right? As we went to a sampling distribution standard deviation, right? So the standard deviation of the means was equal to the standard deviation divided by the square root of n, okay? So this kind of summarizes what that central limit theorem does and what it means for us when we are using it for data purposes and calculating probabilities. So the next video is going to kind of walk you through some problems where we actually get to use this theory and use it to help us calculate some probabilities on things that we weren't able to calculate probabilities on before.